Here is a problem of variable mass system. A rocket is moving vertically upwards with constant velocity v naught by ejecting gases at a constant rate mu kilogram per second. At what velocity with respect to ground should the gases be ejected at any instant t if mass of the system is m naught at t equal to 0? So told that it is moving with uniform velocity. For rocket to move with uniform velocity vertically upward, uh, you know that net force on the rocket should be zero. But the ejected gases, whichever are coming out from the rocket, will develop a thrust upward. The thrust developed by the ejected gases is given by V relative dm by dt. V relative is relative velocity of that thrust, I mean ejected gases with respect to the rocket, V relative. Dm by dt is the rate at which the mass is ejected out. For it to have the constant velocity, the thrust that is upward acting on the rocket should be balanced. Definitely, it should be balanced by the weight of that system at that instant. So, say I can say V naught, for V naught to be constant, the downward mg at any instant should be balanced by V relative dm by dt. So that V relative is what? Suppose if that ejection velocity is V, actually V with respect to ground, ejection velocity is V with respect to ground, then I think we can write V relative as mg equal to V plus V naught dm by dt. We are told that dm by dt is mu, so finally we can write mg equal to V plus V naught into mu. So we would get V we want, because V is the velocity of the gases that are ejected out. V would be mg by mu minus V naught, but m can be written as m naught minus mu t by mu into g minus V naught. So this is the expected velocity of ejection, which is of course a function of time, because we are in this problem seeing that the rocket is maintained to go up with a constant velocity v naught, for which definitely, so as to balance this gravitational force which is varying because mass is decreasing, the thrust also should vary. Here there is next other question. A flat car of mass m naught starts moving to the right due to a constant horizontal force F. Sand spills on the flat car from a stationary hopper. Velocity of loading is constant and equal to mu kilogram per second. Find the time dependence of the velocity and acceleration of the flat car in the process of loading. As you are seeing that the mass is loaded or added into this, in the direction of the car, this mass initially which is falling into the car has no velocity, and velocities of the mass is not described. We can just treat it is just falling at rest onto this car. So we can say that as loading is taking place, the thrust provided by the added mass is not a encouraging thrust, it is discouraging. So we can write that net force on the system as F minus V relative is V, which is velocity of car, of course, because for the particles which are falling, just into this. We are just considering actual velocity to be zero. Hence, the relative velocity magnitude is v itself. So F minus v dm by dt is a force that is equal to product of mass and acceleration of the system. So m dv by dt. This is the equation we get. In the problem, we are asked to give the velocity and acceleration as a function of time. And still further, we can write this as v into mu uh, equal to m dv by dt. Let us rearrange this. We would get dt by m. Here m would be, we can write m as mu naught plus, m naught plus mu t, because we are putting at some t equal to t, all this equation. By then some mass is loaded into it. We rearranged dt by m, and we would get this on the right side as dv by f minus mu v. Let us integrate this on both sides. Initially the mass is m naught, and it is m later after time t. So, and initially the card begins from rest, so 0 to b. Oh, sorry. This is we have to take the limits as time. So t is 0 to t equal to t, let us say. So on the left hand side, I would have 1 by mu ln m naught plus mu t by m naught. On the right side, I would have a minus 1 by mu logarithm of f minus mu v by f. On both sides, I can eliminate mu, and I can rearrange things. I would get m naught plus mu t by m naught equal to f by f minus mu v. So we want to find v. We can write f minus mu v equal to m naught f by m naught plus mu t. I'm going to the next page. So we have f minus mu v equal to m naught f by m naught plus mu t. So let me rearrange. I would have f minus m naught f by m naught plus mu t equal to mu times v, and we would have mu t f by m naught plus mu t multiplied with 1 by mu equal to v. Therefore, we get velocity as ft by m naught plus mu t. That's the velocity. To get acceleration, we can differentiate the velocity with time, or else we can also use, we got the expression that f minus mu v we have, that is equal to ma. So let's also write it as, instead of v, I can put v as a function of time. Just now I got, which is ft by m naught plus mu t by m is, we have it as m naught plus mu t. So let us rearrange the things. We would have m naught plus mu t whole square in denominator. In the numerator, I would have m naught plus f mu t f. So we'll be left with m naught f. So that is the acceleration. The same thing you can arrive using differentiation of v with respect to t. So this is how the acceleration and velocity are the function of time. That means you can see as t is increasing, the acceleration is decreasing. You can see t, of course, velocity should increase, but acceleration will decrease. Acceleration will finally touch. Um, you would get at t equal to infinity, acceleration would become zero. You can also still work with this. F is equal to m naught by t plus mu. So at infinity, t equal to infinity, you will get v becoming equal to v terminal velocity, and that would become equal to f by mu, with acceleration becoming zero. So because mass is keeping on adding, v terminal velocity, I'm just pronouncing it as terminal. Further, there are no changes in the velocity, hence we can call it as terminal velocity. We shall see the next question. A cart loaded with sand moves along a horizontal plane due to a constant force F coinciding in the direction with the cart's velocity vector. In the process, sand spills through a hole in the bottom with a constant velocity mu kilogram per second. Uh, find the acceleration and the velocity of the cart at the moment t. If at the initial moment t equals 0, the cart with loaded sand had a mass m0 and its velocity was equal to 0, the friction to be neglected. So you can visualize a diagram with the cart and having a hole at the bottom, and the cart is pulled with some force. This is a loaded cart. Now this cart at some instant at t equal to t has some velocity v. Now when the cart is having v, the unloading thing which is coming out also will have v. Implies that v relative will become 0. If v relative 0, the thrust that is developed by this is v relative dm by dt, which would be also 0. So there is no force actually to say. So we can write things like this. So force that is exerted by external agent plus this is the thrust developed by this ejected mass or unloaded mass is equal to m dv by dt. So we can write dt by m equal to dv by force. We can write dt by m is what? M is m naught minus mu t, which is equal to should be 1 by f dv. You can integrate from t0 to t and from v0 to v. So we would have what? Minus 1 by mu ln m naught mu t by m naught, that is equal to v by f. So we can write the velocity as therefore v equal to f by mu times ln m naught by m naught minus mu t is the velocity as a function of time. We want acceleration. So acceleration we can write from this. The acceleration is force by mass. So there is no thrust. The force by mass is, we can write m naught minus mu t. So at any instant of time t, this is the acceleration. This is how velocity and acceleration change with time. This is another question. A spaceship of mass m0 moves in the absence of external forces with certain velocity v0. To change the motion direction, a jet engine is switched on. It starts ejecting a gas jet with a velocity u, which is constant relative to the spaceship, and directed right angles to the spaceship motion. The engine is shut down when the mass of the spaceship decreases to m. Through what angle did the motion direction of the spaceship deviate? due to jet engine operation. Very interesting. You got that spaceship. It has a provision so that it can eject the gases. Actually, the spaceship is going with V naught. So the jet ejected, let's say it has some dm. This ejected jet has V naught as a speed, and it is having some speed u relative to the spaceship. Now we are going to work in the spaceship frame. U is ejected out. So because of this ejection, there is some force for this. Say there is some force on jet F to the right. This force is there on the jet, in the sense in reaction jet also will give a force to the spaceship in this direction, and the ejected jet is giving force which is perpendicular to V naught, hence V naught magnitude remains the same. So because of this additional force directed always perpendicular to V naught, the spaceship will move along a curve which can be described with some center and radius of curvature. We can visualize um, the spaceship. Say initially the spaceship has some V naught like this. Over certain interval, let the spaceship get V naught like this. As the spaceship along its path is maintaining a constant speed, there is some force due to the jet ejected. Jet is ejected this side, but the force due to the jet would be acting this way. We can say this force provide necessary centripetal force at any instant. So this force is u dm by dt. But I put a negative sign because m is decreasing, because already the direction of force is indicated. So minus u dm by dt is actually a positive value. This is providing necessary centripetal force for this to move along the curve with speed v. So mv naught square by r. Let us say r is the radius of curvature. So let's rearrange things. We would get minus ru dm by m v naught square dt. Let us integrate this. The mass is initially m naught. It is now becoming m in, say, time interval t. As v naught is a constant, it is out of the integral. So minus ru, this is logarithm m by m naught v naught square into t. So, but as it is, we are asked to tell the angle through which this got deviated. The angle through which this got deviated, suppose if the V naught turns through an angle theta from the initial direction, this is the initial direction. So say center of curvature is there somewhere here. At the center, this would have traversed an angle theta. Therefore, we can write that r theta should be, as it is moving with a constant speed along the curve, we can write the distance traversed along the circumference of that curve is v naught t. So that should be length of the arc, but we know that length of the arc is r theta. So we can write r theta is equal to v naught into the t. The t is, we can rearrange and write ru ln m naught by m by v naught square is the time from the result we got. So we can cancel that v naught, we can rearrange, cancel that r on both sides. So u by v naught ln m naught by m would be the angle. Of course, this is in radians, through which this deviate or change its direction. This problem can also be achieved in the other way. I'm going to write somewhere here. Uh, say the rotating vector here is v naught bar. Now, if I consider the tangential velocity to the circle, the rotating vector is v naught bar. So we got that minus u dm by dt is the force. We can write that as m times v bar, that is v naught bar cross omega bar. The angle between v naught bar cross omega bar is 90 degrees. So I'm showing the magnitude here, of course. So minus u dm by dt is equal to mv naught. Omega can be d theta by dt, where d theta by dt or omega is angular velocity for v naught bar's rotation. V naught bar, you can visualize it as a vector and it is a rotating vector. If its rotation rate is d theta by dt, we can write that omega is d theta by dt. So let us again rearrange the things. We can remove that dt. We can rearrange this as m v naught d theta. Things are changing from m naught to m, from 0 to theta. So we can write ln m naught by m in by v naught should be theta from this. This is the angle through which the velocity vector v naught bar got deviated.